Hi everyone, welcome back to Bevy Basics. Before we dive into today's content, I want to extend a huge thank you to everyone who has been following along. We apologize for the gap since the last video. We've been working hard on our upcoming video game, and that's been taking almost all of our time. This episode is going to focus on the coordination, execution, and communication of systems in Bevy, and cover Bevy's intermediate APIs for managing game logic. We will cover state, events, and run conditions. As always, we'll wrap up with a code example. First, let's start with a recap. In the last episode, we covered scheduling and system ordering. If you haven't watched that yet, I highly recommend you check it out before watching this video. Having a strong understanding of schedules and system ordering in Bevy will help you grasp the concepts in this episode. Today, we're exploring 3 more concepts that are pivotal to efficient game development in Bevy. So let's dive in. By using these concepts, Bevy provides a structured yet flexible way to control how and when different parts of your game react and interact. States, events, and run conditions each play a unique role in this orchestration. To start, let's answer the question of why we would use these features. First, state, events, and run conditions can be used to control how and when different parts of your games react and interact. Although these features are not strictly required to make a game, they can greatly streamline your game logic. More specifically, these features all enhance ergonomics, minimize boilerplate, and decrease the amount of tight coupling in your codebase. As such, I highly recommend you utilize these concepts in order to achieve a more organized, maintainable, and efficient game development process. Let's start by learning about state. State management is central to most games, defining the different phases or modes of gameplay. In general, state can be implemented in various ways depending on the programming language, framework, or the specific requirements of the application. Bevy provides a built-in concept of state. In Bevy, state is a finite state machine whose transitions have associated schedules on enter, my state, and on exit, my state. One example of how you might use state in your game is by defining a GameState enum that has variants for main menu, in-game, paused, and so on. Using Bevy's built-in state gives us an ergonomic way to control running systems based on the current state of the game and state transitions. First, let's talk about state transitions. The on-enter and on-exit schedules in Bevy can be used to run specific systems when entering or exiting a given state. When the application state changes to the specified state variant, systems added to the on-enter variant schedule are executed. When the application transitions away from a specified state, systems with on-exit variant are executed. These schedules are especially useful for initializing or cleaning up resources that are only relevant to specific states. For example, displaying or hiding a specific interface when UI state changes. Bevy automatically manages the creation and execution of these schedules for you. If you remember from the last episode, all state transition schedules run before the update schedule each frame. So let's dive into the APIs for state management in Bevy. You can derive states on any struct or enum that implements equals, hash, and default, among a couple other required traits. The default trait defines the starting state. Each variant of an enum is a separate state, thus the name states. Once you have defined the data for your state, you can use the add state : my state API to initialize the single state. Calling this API will initialize 2 resources for managing the state and add the apply state transition function to the state transition schedule, which will run the on-enter state and on-exit state for each variant of your enum or struct. And that's all you need to know about state to add it to your application. But how about accessing and changing state? You can access the current state of type T with the state T resource and the queued state with the next state T resource. Here, the generic type T is just the concrete type that you defined before and derived states on. Let's take a look at an example of a pause system that changes the game state. In systems, you can use res state GameState to access the current state, and res mute next state GameState to update the state. Here, the state and next state structs wrap the internal state type. We can use the .get API on the state T resource and the .set API on the next state T resource. In this example, we are toggling between the state in-game and the state paused when the user presses escape. Now let's move on to events. Bevy events are a mechanism to send and receive messages between systems that can react to specific occurrences within the game, like user input, collisions, or custom events. Events allow for decoupled communication, where one system can send an event without knowing which systems, if any, might respond to it. Utilizing events in your architecture can enhance modularity. For example, systems that manage visual effects can be defined in a separate plugin and be triggered through events. Events in Bevy are strongly typed, meaning each event type is a struct or enum. When creating a new event, derive the event trait. Just like state, you will register the event type to your Bevy app. The API to do so is add_event: my event. Events are sent with an event writer T, where T is the generic type of your concrete event type. Systems can then be read using an event reader T as a system parameter. Again, T is the concrete event type that you define and derive event on. Let's take a look at an example. Here, one system is reading collision events which are sent by another system when collisions are detected. The .send API is used to send an event with an event writer, and the .read API is used to iterate over all new events of the given type with an event reader. Event readers and event writers are automatically injected as parameters to systems, just like queries, resources, etc. It's critical to understand how the event reader and event writer APIs work. First, know that every event reader of type T tracks the events it has consumed independently. This means that if you read events in systems A and B, and system A runs before B, system B will still receive all the events. Second, know that events are automatically cleared by Bevy. Events are dropped so that the event queues don't grow forever. Usually, events aren't deleted until after the end of the next frame, which allows systems that run before the system that sent the event to read the event on the next frame. Finally, let's move on to the final topic, which is run conditions. In the previous episode, we learned how to use Bevy's before, after, and chain APIs on systems to define ordering. Run conditions are simply another API that can be used to configure systems and orchestrate when they run. Specifically, run conditions allow you to control when systems run. They are powerful when combined with states and events. We can apply run conditions using the .runIf API, and run conditions will be evaluated at runtime. Creating a run condition is as simple as defining a Bevy system that returns true or false. The condition will be evaluated when passed to runIf once right before the system or group of systems run. Just like with the .chain APIs, runIf can be applied to a grouping of systems. So for example, you might have a tuple system A, system B, and then call .runIf on it and say paused, meaning that these two systems will only run if the game state is paused. Bevy also provides various helper APIs for working with run conditions. In fact, most of the time you use run conditions, you will probably do so without actually writing a system for the run condition. Instead, you will write runIf in state and then specify a state variant, or say runIf on event and specify an event. Run conditions can also be combined with or else and then. Or else is a run condition combinator that only evaluates the second condition if the first condition returns false. And then is also a run condition combinator that only evaluates the second condition if the first condition returns true. This is very similar to the lazy evaluation of normal Boolean operators, and it allows you to combine run conditions efficiently. For example, you might say runIf in state GameState paused, or else in state GameState in game, meaning this system would run when the game state is paused or the game state is in game, but it would not run if the game state is GameOver or another variant. In summary, run conditions allow us to decouple the logic that determines when a system runs from the logic of the system itself. This allows us to easily define a system once and potentially run it in multiple different schedules or on multiple different conditions. For example, we might want to run the spawn spaceship system in two different scenarios. When the game loads, which can be accomplished by adding it to the post-startup schedule, and when the game restarts after the player loses. which could be accomplished by running it in the update schedule when a restart event is received. Let's use the new APIs that we've learned by applying the concepts to a game example. As always, I recommend you follow along during the code example. You can find the complete source code for this episode and all previous episodes on GitHub. To jump to the code for this episode, simply clone the repository to your local machine. Start with the code from the previous episode, episode 4, which is in the episode 4 subdirectory. The package can be run with cargo run -p episode 4. Make your modifications there, and then if you run into any issues, compare your code to the complete source code in episode 5. It's time to move on to this episode's code example. First up, we are going to be adding a GameState state to our app. We'll use that to implement pause functionality such that all systems in our in-game system set only run when the game state is in-game. The first thing we are going to do is create a state.rs file. The file will define a new plugin called state plugin. The first thing that we will define in this file is an enum GameState, which will derive states. The enum will have 3 variants: in-game, the default state, paused, and GameOver. The states trait requires a number of other traits such as equals, partial equals, hash, and default. We'll go ahead and pull those in now. Next, we'll define the struct for the state plugin. As usual, we'll implement the plugin trait for state plugin by defining the build method. The build method will add the state to the app. This call to add state behind the scenes will initialize 2 resources for managing the state and add the apply state transition system to the state transition schedule, which will run the on-enter game state and on-exit game state schedules. As we mentioned in the slides, this is what Bevy does for us automatically. It inserts the new schedules and creates resources for us so that we can easily use state in our application without managing those things manually ourselves. Next, we'll add a single system to update called GameState input events. This system will take a mutable reference to next state GameState such that it can update the game state, and an immutable reference to state GameState so that it can check the current value of GameState. The system will simply read keyboard input, and if the user has just pressed escape, the state will be toggled between paused and in-game. To do this, we'll simply match on the value of the current state and use the set and get APIs on the next state and state resources. Next, we'll need to make sure to add the plugin domain.rs so that our Bevy application will run this new system and add the state to our app. Now, if we were to run our app, we'll technically be able to press escape and toggle between in-game and paused, but nothing will happen. This is because we aren't doing anything as a result of the state being set to paused. Now let's go ahead and actually implement the paused functionality. You may be surprised that we can do this with just a single line of code. If you remember from episode 4, on ordering systems, we defined a system set called in-game set, and then we configured 4 variants: despawn entities, user input, entity updates, and collision detection. We used this system set to define system orderings across plugins. More specifically, we added the .inset, in-game set, whatever variant after each of our game logic systems to define when the system should run. As a result, we can simply update the configuration of in-game set in schedule.rs with a run condition to add pause functionality. Yes, that's right. Run conditions can be used on system sets, just like chain and the other system APIs. In this case, we'll add run if, in state, game state, in-game, such that it is applied to all variants of the in-game set that we're configuring for the update schedule. This way, when the game state becomes paused, the run condition will be evaluated to false at runtime, and all systems that run in the in-game set will no longer be executed by Bevy. Now, if we go ahead and run the game, we can press escape, and we should see that the spaceship will no longer respond to input, and the asteroids will stop moving. Next, now that we have the pause functionality implemented, we're going to get some hands-on practice with events. We'll upgrade our collision detection logic to be much more robust by separating the detection of collisions from the results of those collisions using an event. We'll also switch to using a health-based damage system, which will enhance the gameplay by requiring the player to fire multiple missiles in order to destroy asteroids. We'll also use the very same components for the spaceship, such that it can sustain multiple asteroid collisions before being destroyed. We'll start by adding a new file, health.rs, which we will use to define a component for health that will be shared across multiple entities: missiles, asteroids, and the spaceship. For now, since this file only defines a single component that will be imported by other files, we don't need to define a plugin. However, later on, if we define systems such as health regeneration, etc., we could definitely define a plugin and add them here. Note, when I defined health here, I forgot to make the value field public. Don't worry, we'll come back and fix that later. Now that we have the health component, let's go into collision detection and make some changes to upgrade the logic. We're going to start by defining two new structs. First, a component, collision damage, that we can add to any entities such that those entities deal damage when another entity collides with them. For example, we could add collision damage to our missiles such that missiles deal damage to asteroids. The second struct will be our first event, collision event, which will store the entity that triggered the collision and the entity that it collided with. In other words, self and other. To round out the definitions, we'll generate the new methods for each of these structs for more concise construction. Great, now we have our data structures in place. Let's go ahead and make updates to the existing handle collision system to instead send a collision event. This will allow any number of downstream systems to consume that event. For example, we may want to deal damage, play a sound, increase the score, or any other number of things as a result of the collision, and we won't want to do all of these things in a single system. To do this, we'll swap out the command struct in handle collisions to be an event writer of collision event. Then, instead of just calling commands.despawn and immediately despawning the entity, we'll go ahead and send an event, collision event, that specifies the entity and the other entity that it collided with. Now, to actually apply the damage, we'll define a new system, apply collision damage. The first parameter of the system will be an event reader for the collision event type. We'll also specify two queries, one mutable health query and one immutable query for collision damage. In the body of the system, we'll loop over all the collision events. Then, we'll pull out the health and the collision damage by looking up based on the entity and the collided entity, the component, using queries. Then, we'll decrement the value of health by the collision damage amount. Note that here we're using the .get and .getMute APIs on queries to efficiently look up entities with the specified components using the entity ID. This is a common pattern when you know a specific entity ID and you want to look up a component for that entity. As we can see, the code is not compiling because we forgot to make the health field value public. Let's go ahead and do that. Now we'll go up to our plugin definition and update the add systems call. We'll add the new apply collision damage after the handle collisions for asteroids and spaceships. We can do this by putting the handle collisions in a tuple. Then if we call .chain on all of them, we can use the nested system ordering. Here, apply collision damage will run after apply collisions for asteroids and spaceships, but handle collisions for asteroids and spaceships can still run in parallel. We'll also want to register the event type, collision event. If we forget to do this, your application will crash at startup. Note, we'll also want to add handle collisions for missiles here. Before, we didn't care about destroying missiles because asteroids were instantly despawned. But with the new health and collision damage systems, we'd like it to be so that when you fire missiles, they destroy themselves upon impact with an asteroid, dealing a certain amount of damage. Without this, missiles would never be destroyed and would deal damage to asteroids each frame while colliding. Finally, we'll also move these systems to run in the in-game set entity updates since we aren't directly despawning the entities anymore. Great, now our systems for handling collisions are in place, and they can utilize the new health and collision damage components in order to deal damage over time when objects collide with each other. However, we still haven't added those components to any of the entities, so let's go ahead and do that now. First, we'll go to asteroid.rs and add two constants for health and collision damage. Then, inside of commands.spawn, where we add the other components, we'll add health with the specified health constant amount and collision damage with the specified collision damage constant. We'll need to import these to the file, and then everything should be good to go for asteroids. Then we can move on to the spaceship.rs file. Again, we'll add 2 constants for the spaceship health and collision damage, and 2 constants for the missile health and collision damage. Then in spawn spaceship, we'll do the same thing, pulling in the spaceship health and the spaceship collision damage. Finally, after we've added this all to spawn spaceship, we'll import the components and then go down to the spawn missile logic where we have the weapon controls and pull in health and collision damage. This way, missiles, the spaceship, and asteroids will all have the components health and collision damage, and the queries for collision detection will be able to pull in those entities, the health and the collision damage for all of those successfully. I want to call out and just really quickly mention that we've chosen, what we find to be reasonable values for health and collision damage, such that missiles are immediately going to be destroyed because they have 1 health, and that missiles deal about 5 collision damage. That means that a dozen or so missiles will destroy an asteroid, and then that the spaceship will be destroyed if it collides with 3 asteroids because it has 100 health and each asteroid deals 35 collision damage. You can tweak these in your own implementation to be whatever values you think is most interesting. Cool. So if we run the game now, everything's going to compile. However, nothing's going to be destroyed if you shoot some missiles at the asteroids. This is because we aren't doing anything if the health reaches 0 or drops below 0. In order to fix this, we need to add a new system. Let's go into despawn.rs and add a new system called despawn dead entities. This system is simply going to loop over all entities with health. That's going to be our missiles, the spaceship, and the asteroids. And then it's going to despawn the entity if the health reaches 0 or drops below 0. And with that, we should be able to run our game and see our health and damage systems in action. Before we move on and implement the functionality for triggering game over, I'd like to do a quick review of the changes we made so far. A great way to do that is to look at the Diff. We've added the mod for health and state, and we've added the state plugin to our app. Then, in collision detection, we've defined collision damage and collision event such that we have a component for dealing damage when things collide, and we have an event to fire when that collision happens. We've added the apply collision damage system and handled collisions for asteroids, spaceships, and missiles. We've registered the collision event with add event. We've modified handled collisions to use the new event writer to send collision events, and we have defined the system apply collision damage, which reads all the events, gets the health and collision damage, and then decreases the health value by the collision damage amount. In the asteroids file, we've added the health and collision damage components. Similarly, in spaceship.rs, we've added the missile health and the spaceship health, the spaceship damage, and the missile collision damage. With all of that in place, we've gone in despawn RS and added a new system, despawn dead entities, that checks the health of all entities with the health component and despawns them when they reach 0 using commands entity despawn recursive. And now let's move back over to state.rs. This is where we implemented the pause functionality. As you remember in the beginning, we said we'd only worry about in-game and paused for now. And that's what we did by adding the pause functionality and allowing the user to toggle between in-game and paused using escape. But now, let's move on. Let's focus on the game over state and allow the player to continue playing after the spaceship is destroyed. That is, the spaceship's health reaches 0 and is despawned. This new stage will despawn all the asteroids and missiles and then respawn the spaceship. To do this, we'll use our game over state. First, we need to detect when the game should be over. We'll do this by running a system update in the spaceship RRS file and simply check, is the spaceship spawned or does it not exist? We'll create the system with 2 parameters. First, the next state mutable resource that will allow us to queue state transitions to the game state, and then a query, empty query, since we don't care about any of the components, with spaceship. We'll use this query to check if the spaceship exists or not. That is, the query for with spaceship is empty, using getSingle. If getSingle returns an error, we know that the spaceship does not exist, and thus we can call .set on next state in order to queue the state transition for GameState, such that it transitions to game over. We'll add the system destroy spaceship to the spaceship plugin in the update schedule. Next, we'll want to respawn the spaceship and despawn all the asteroids and missiles that are currently spawned. To do this, let's simply spawn the spaceship again when we enter the game state GameOver. This can be done by specifying the onEnter GameState GameOver schedule when we add the system. As we covered in the slides, this means the system will run once when the state transitions to GameOver. Similarly, in Despawn.rs, let's add a new system called Despawn All Entities to the same onEnter GameState GameOver. This Despawn Entities function can simply loop over anything with health and despawn it recursively. If we run the game now, the spaceship will respawn and the missiles and asteroids will disappear. But we won't be able to continue playing. That's because we're stuck in the game state GameOver. Let's fix this by adding a new system to state.rs. We'll do this by adding a system called transition to in-game that will unconditionally set the next state of game state to be in-game. But wouldn't this always run? Well, we can use run conditions to make it run conditionally. So let's add that system to the update schedule, but only run that system if we are currently in the game state GameOver. Thus, one time when we enter the GameOver state, we'll immediately transition back to game state in-game. This is the power of run conditions. We can have game logic for a system, and then we can determine when it runs based on some criteria, such as what state it's in. In a real game, you'd probably want to pause the game and have the player press a button to restart. But for our purposes, this should work just fine. And with that, we can run the game and we would see the asteroids continue to spawn after the spaceship respawns, allowing the player to continue playing. With this in place, we are very close to having an actual game. You can imagine adding a score system, some simple UI, and maybe a couple power-ups. If you're feeling adventurous, I'd encourage you to explore adding those features on your own. And that concludes this episode's code example. In future videos, we'll cover topics such as local resources, change detection, and third-party plugins. Before we end the video, I'd also like to mention that if you're interested in participating in upcoming playtests for our game, we recently posted a thread in project collaboration on the Bevy Discord. Feel free to check it out and reply there if you're interested. As always, thank you all for watching. I want to, give you a little bit of insight of why we've decided to take a step back from releasing videos so regularly, and the reason is that it was eating in significantly to the amount of time that we had to work on our game, and right now that's taking top priority. Producing each of these videos involves a significant amount of effort. It takes multiple days if you include writing the transcripts, preparing the slides, creating the code examples, recording the audio, editing the audio, and editing the video. While the frequency of future videos might not be as high going forward, we are committed to maintaining the quality that you've come to expect from this channel, and we hope to continue delivering high-quality videos as time allows. If you'd like to be notified and keep up to date with when those videos come out, please subscribe to the channel. And as always, I'll see you all in the next video, whenever that may be.